Assalamu alaikum wa rahmatullahi wa barakatuh. This is the fifth video of chapter 11, Work and Energy. At the end of this video, you're going to be able to apply the work-energy theorem. Let's remember the main ideas that we took in the last videos. We have investigated work and identified it as a mechanism for transferring energy into a system. As you see in the following two screenshots of the motion of a man pushing a cart. A work is done on the cart. The cart moves on and its speed increases. So we say that one of the possible outcomes of doing work on a system is that the system changes its speed. In this section, we're going to investigate that there is a relation between the work and the speed, thus the kinetic energy, which is called the work-energy theory. Consider a block of mass m moving through a linear path AB under the action of the external constant forces F1, F2, etc. Fn. Applying Newton's second law gives sum of F external equals to ma vector. Then the sum of forces equals to F1 plus F2 plus etc. Fn equals to ma, which is constant. Then the acceleration is constant and the motion is uniformly varied rectilinear motion. Multiplying both sides with AB gives F1 plus F2 plus etc. dot product with AB vector equals to ma vector dot AB vector. Expanding the dot product, we get F1 dot AB plus F2 dot AB plus etc. Fn dot AB equals to MAD. D is AB. A and D are algebraic values. Remember that we aim to find a relation between the kinetic energy and work. So, re-mentioning that the motion is uniformly varied rectilinear motion, how may this idea help us to find this relation? Good. We know that V final squared minus V initial squared equals to 2AD. Instead of A, the acceleration, we can replace it by the expression VB squared minus VA squared over 2D. Let's try it and see what may happen. Instead of F1AB, F2AB, Fnab, we can write work done by force 1, work done by the force 2, etc. equals to m times the expression of A times the distance d. The first part gives us the sum of work done by the external forces, and the second part of this equality gives us mass into half Vb squared minus half Va squared. This part can be written as half mVb squared minus half mVa squared, where B represents the final position and A represents the initial position. We can write it as delta kinetic energy, and here comes the work energy theorem, or what is called by the kinetic energy theorem. The sum of work done by external forces from A to B equals to the variation in kinetic energy between A and B. Let's make a practice. Ali is pulling a chariot from rest a distance AB such that AB equals 10 meters by applying a force F vector making angle 60 degrees with the horizontal plane. During its motion, the chariot of mass m equals to 15 kilograms is under the action of weight mg, friction force, which is 20 Newton, normal reaction, and the force F of magnitude 80 newtons. The first question. Determine the net work done by the external forces on the chariot. We start with representing the forces acting on the chariot. The normal reaction is perpendicular to the displacement and directed upward, while the friction is parallel to the displacement but opposite to it. Weight, or mg, is downward, also perpendicular to the displacement. The force F is oblique force, making angle 60 degrees with the horizontal. Now the work done by N and mg is 0 since they are perpendicular to the displacement. The work done by friction is minus FAB equals to minus 200 joules. The work done by the force F, which makes angle 60 degrees, is FAB cosine 60, and the answer is 400 joules. The sum of work done by these external forces on AB is 200 joules. The second part, by applying the work energy theorem, deduce the speed of the chariot at point B, which is the final position. In this case, we're going to write the theorem as kinetic energy B minus kinetic energy A equals to the sum of work done by external forces from A to B, then half mv B squared minus half mv A squared equals to the sum of the work done by external forces that we have found its value in the previous part. But since the chariot starts from rest, then kinetic energy at A is 0. Then V final after calculation is 5.16 meters per second. The second application, a particle of mass m is released from rest from a height HA equals to 8 meters above ground along a curvilinear path AB. Neglect all frictional forces and take G equals 10 meters per second. Using the work energy theorem, calculate the speed of the particle at point B. We should start with the work energy theorem, then it is written as half mvb squared minus half mva squared. The forces acting on this particle along its path are just the normal reaction and mg, so we can write it as the work done by mg plus the work done by n. The kinetic energy at A is 0 since it starts from rest. The work done by n is 0 since n is perpendicular to the displacement. It is written as half mvb squared equals to mgha. Dividing both sides by mass m, we get vb equals to the radical 2gha. Finally, it's 12.65 meters per second. This is enough for today. I want you please to study the areas of this lesson. This is the end of part 5. Thank you for watching.